Good day, everyone. Today, we will explore how the limits of algebraic functions are applied to solve real-life problems. Be sure to have your pen, paper, and graphing tools such as Desmos or GeoGebra ready as we uncover the importance of understanding limits of algebraic functions and their practical significance. Let's begin by looking at a real-world scenario involving the flow of water. As water flows from the Kitindai River, it forms pools along its path. The amount of water in a particular pool after T hours is modeled by the following polynomial function. Wt equals 100T minus 2T cubed. Here, Wt represents the volume of water in liters in the pool at time t in hours. Our goal is to know what happens to the volume of water in the pool as time progresses indefinitely. We will apply the concept of limits to determine the behavior of the function as t increases. Take a moment to sketch this function using your graphing tool. How do you think the pool's capacity changes over time? We'll find out shortly. To solve this problem, you can either use a table of values or graph the function using your graphing tool to observe the behavior of Wt as t approaches positive infinity. Let's start by creating a table of values. We'll substitute increasing values of t into the function, specifically evaluating it at t equals 0, 1, 5, 10, 15, 20, and 100. Notice that as t increases, the resulting values of Wt decrease significantly without bound. This suggests that the limits of Wt as t approaches positive infinity is negative infinity. In other words, the volume of water decreases indefinitely as time progresses. Now let's confirm this result by examining the graph of the function. From the graph, we can clearly see that the curve continues to drop downward as t increases, reinforcing our conclusion that the limit of Wt as t approaches positive infinity is indeed negative infinity. But how do we interpret the result of negative infinity in the context of our problem? Keep in mind that the natural pool has a limited capacity. As the volume of water increases, the pool eventually reaches its maximum capacity. Beyond this point, as time progresses, the pool could begin to overflow or reach a breaking point. In this scenario, the limit approaching negative infinity suggests that the volume continues to decrease after the pool reaches its maximum capacity, possibly due to water spilling over or escaping through other means. Now let's move on to another scenario, this time involving medication in the bloodstream. After taking medication, the concentration of the drug in the bloodstream decreases over time. The concentration C of T in milligrams per liter after T hours is given by the function C of T equals 50 over 1 plus 2T. Question 1. What is the initial concentration of the drug in the bloodstream at T equals 0? Question 2. What happens to the drug concentration as time approaches infinity? Now, to address the questions, we can use limits. Using limits, we can analyze how the concentration changes both at the beginning and as time goes on. Take a few minutes to graph the function and explore its behavior as t increases. First, we find the initial concentration of the drug in the bloodstream at t equals 0 using the limit law. The limit of f of x as x approaches a is equal to f of a. Substituting t equals 0 into the function, we get c of 0 equals 50. Therefore, the initial concentration of the drug in the bloodstream is 50 milligrams per liter. Now let's determine the drug concentration as t approaches positive infinity. To do this, it's helpful to use graphing tools to visualize the behavior of C of t over time. From the graph, we can confirm that when t equals 0, C of t is indeed 50. Additionally, we observe that the graph approaches the horizontal axis but never touches it, indicating that the function is asymptotic to 0. Thus, we can conclude that the limit of C of t as t approaches positive infinity equals 0. This means that as time progresses, the concentration of the drug in the bloodstream gradually decreases to such a low level that it becomes negligible or virtually absent. Thank you for your active participation today. I look forward to seeing you apply these concepts in future lessons and, even more importantly, in your future careers where your skills can contribute to our country's sustainable development.